So today I'll start a couple of, it will be at least a few lectures on the other part of preliminaries, namely some basics of metric spaces and this would come under the more general topic would be point set topology, but we are just going to confine ourselves to metric spaces. So as with the linear algebra part, I'll not be giving proofs of many things. I'll refer you to Rudin, and I'll just write down the concepts and results that we'll need. So let's start. A metric space is a pair consisting of a set and a function where D from x cross x to 0 infinity is a distance function or metric as defined earlier. Yeah. So now the moment we have this distance function, there are lots of things, lots of concepts which arise associated to this. So let's start listing these. The first thing is definitions and properties the fundamental concept in a metric space is that of a ball. So let P be a point in X and R a positive number. The open ball of radius R centered at P is the set BPR, set of all x in capital X such that distance between X and P is strictly less than R. And the closed ball is closed ball with radius R centered at P is the set. Now here I'll just use the same notation for the open ball and put a line on top of that. Right now this is just notation, but we know that actually putting a line on a set has a specific mathematical meaning. Namely, we would be taking the closure of the set. So and that in fact the closure of this open ball will turn out to be whatever I am going to write on the right side, but for now let's take it as a definition. So here I include the distance. The distance is allowed to be equal to R as well. Okay, so the concept of an open ball is a fundamental thing. Once we have that, we can define the notion of an open set. U is open if for every P in X there exists R greater than 0 such that BP, not X, every P in U, there exists R greater than 0 such that, so if I take any point in U, I should be able to put a small open ball centered at that point, which is entirely contained in U. So the ball of radius R is contained in U. In general, if S is a subset of X and P is a point in S, P is said to be an interior point of S if there exists R greater than 0 such that BPR is contained in S. So even if a set is not open, it might still contain some points which have this property. So those points are called interior points. And the collection of all interior points is called the interior of S. The interior of S denoted by S with a small circle on top is the collection of all interior points of S. So let me add as a remark this, when even if the set is not open, if I look at this set of all interior points, S interior is an open set. That is one thing. The second thing is that U is open if and only if its interior is the whole set. So both of these are easy things which you can check. Right, so that was an open set. Next, S contained in X is closed if S is equal to X minus S is open. So now there's another way of formulating this condition, the condition of being closed. For that, let's define what an accumulation point of a set is. P in X is an accumulation point. Accumulation point of S if for all r greater than 0 let me write it in a slightly different way. If the following holds. If r greater than 0, then there exists Q in S intersection BPR and this Q should not be equal to P. So in other words, if I take any ball around P, however small the radius, here the point is that R can be as small as we like. Even if I take a tiny ball around P, that ball should contain a point from S. That's what this intersection means. And that point, point which is different from P itself. Of course, P belongs to the ball and P belongs to right. No, I'm not assuming that P belongs to S. Yeah. So that I want something different from P, but and that point should be, yeah. So if the case, see, P can be either in S or it need not be in S. Even if P is in S, it's not automatically an accumulation point because we demand that this Q should be different from P. So according to this definition, remark, if S is finite, it cannot have any accumulation points. Well, simply because I can take the radius to be, say, 1 over n equals 1, 2, 3 and so on, and those each one of them should contain some point from S different from P. So you would be forced to have infinitely many points by yeah, so you would be forced to have infinitely many points in S. So that's the reason why this cannot happen. Now, as I said, the notion of a closed set can be formulated as follows. So, a proposition S is closed if and only if it contains all its accumulation points. So as an example, finite sets are closed. As we remarked in the just in the previous page, finite sets do not have any accumulation points. So this condition that it contains all its accumulation points is vacuously true. Therefore, its finite sets are closed. So sometimes in order to check that a set is closed, one has two options of proving such a statement. One is to take its complement and see that that's open. The other way is to look at an accumulation point of the set and try to prove that that accumulation point belongs to the set. Okay. The next thing is let Y, so I already have a metric space XD. So let me now I'll consider two metric spaces X dx and Y dy be metric spaces. A function f from x to y is continuous if f inverse u is open whenever U is open. So the inverse image of open sets should be open. Then we say that the function is continuous. Now here we are talking about continuous on the whole set X, not continuity at a point. Right. So as sometimes this one can use this definition, but there are our familiar epsilon delta definition and sequential continuity as well. So let me mention those things. So to talk about sequential continuity, a sequence is any sequence is a sequence is just a subset of X indexed by the natural numbers. Is any subset of the form Xn n equals 1, 2, etc. We don't demand that the xn's are distinct or anything like that. So as, all the xn's might be equal to a single point. So it's just that the countable, essentially a countable subset of X is called a sequence, but a sequence is something slightly more in the sense that we have indexed, a sequence comes with an indexing. When we say a countable subset, we don't necessarily have in mind a specific indexing of the sequence Xn converges to P if given epsilon greater than 0, there exists capital N such that distance between Xn and P is less than epsilon whenever N is bigger than capital N. Now, so let's return back to continuity. So, the following are equivalent. A, f from x to y is continuous. B, if Xn, by the way, here we write this as if Xn converges to P, we write Xn converge with an arrow and P. That's shorthand notation for saying that Xn converges to P. If Xn is any sequence in X with Xn converging to some point P, then f of Xn should converge to f of P. This turns out to be a very useful way of checking continuity. I mean, it's just a matter of notation. It's really not that different from either of those two. But this way of thinking in terms of sequences sometimes clarifies things quite a bit. The third equivalent condition is our epsilon delta condition of continuity. So let's see. Given epsilon greater than 0, I should first start with, before epsilon, I should start with a point. Let P belong to P in X be any point given epsilon greater than 0, there exists delta greater than 0 such that whenever distance between X and P is less than delta, we have distance between f of X and f of P less than epsilon. So the open set definition, the sequence definition, and the epsilon delta definition of continuity are all equivalent. And as I said, here I'm talking about continuity on the whole domains X. We can easily modify these for continuity at a point. Even the open set definition can be formulated for continuity at a point, but let me just take one of these. So, remark, f is continuous P as opposed to just saying continuous. F is continuous at P in X if B, let me take the sequence definition, if B holds for P. So what does this mean? It just means that if I take any sequence converging to the given point P, here earlier there was no restriction on the sequence or the point P. Any sequence converging to any point, one had to have this condition, this thing here, but now I fix P and say that for any sequence converging to P, I demand that f of X converges to f of P. One has similar conditions, equivalent conditions in terms of the epsilon delta definition or the open set definition as well. All right, so let me stop here. Next time I'll continue with my discussion of metric space topology, talk a bit about uniform continuity, compact sets, etc., and connected sets. Okay, thank you.